Hello everyone, focusing on the definition of inductance, quality factor, rated, and saturation current. Let's begin. Here's today's agenda. As I mentioned, we're going to define both inductance and inductor, different types of inductors, and what effects does the core material and wire type have in this type of component. As you can see, we're also going to go through topics such as Q factor, hard and soft ferrites, hysteresis loop, saturation, frequency and temperature effects in permeability, direct current resistance, skin effect, rated current, and self-resonant frequency. Let's start by defining the inductor. This is a passive electrical component that stores energy in a magnetic field when an electric current flows through it. The inductance limits the change in current once a voltage is applied. 1 Henry is a measure of inductance of a closed circuit that produces 1 volt when the current varies 1 ampere per second. And also, 1 Henry is equal to 1 Weber per ampere. An inductor basically consists of a coil conducting material, which typically is insulated copper wire wrapped around a ferromagnetic core. There are also different types of inductors based on this core. Some examples of these types are shielded, unshielded, and air core. As I mentioned before, the inductance is measured in henries, and it can be calculated with the following formula. Once we have parameters such as the permeability of free space, mu sub 0, the relative permeability to air, mu sub r, the effective cross-sectional area, A sub e, the number of turns squared, and the effective magnetic path length, L sub e. We have to be very careful when we calculate this inductance due to the fact that inductors are temperature and frequency sensitive. This means that the inductance value is valid only at a given frequency and temperature. If one of these factors is changed, the inductance changes as well. Always keep this in mind. Now, let's talk about the Q factor, which is the quality factor on an inductor. This is the ratio of its inductive reactance to its AC resistance at a given frequency. In other words, it is the ratio between the stored energy, which is the reactance, X of L, and the losses, in this case, R. The higher the Q factor on an inductor means the closer that it approaches the behavior of an ideal inductor. This translates to the inductor's efficiency. Calculation of the reactance can be done by multiplying 2 times pi times the frequency in hertz times the inductance value in henries. All the loss components can be combined into a loss resistance, in this case R. This is primarily responsible for defining the quality of the inductor. If the inductor is used at higher frequencies, the losses increase rapidly. Unfortunately, mathematical determination of this loss resistance is not possible. Therefore, inductors are usually measured over the entire frequency range with an impedance analyzer, which provides the individual components such as reactance, resistance, and impedance. of course at a given frequency. When we have filtering applications, a lower Q factor would be needed, whereas when we need a storage inductor, a higher Q factor would be required. There are two main factors that define an inductor's behavior. On the left side of the diagram, we have the core, which controls the saturation current of the inductor, and it can be made from hard ferrites such as iron powder and other alloys. And also there are soft ferrites. Some examples would be manganese zinc and nickel zinc ferrites. We will review the main differences between each of them. The other main factors that contributes to the inductor's behavior would be the wire, as shown on the right side of the diagram. This defines the rated current value that the inductor has. And this wire can be round or flat, depending on each application. We will also review each of them to know their main characteristics. First of all, let's take a look at the core and its behavior. You can see on the screen the commonly known hysteresis curve, also known as the VH curve. It shows the magnetic flux density as a function of an imposed magnetic field. This profile is dependent on the core material of each inductor. According to the value of the coercive field strength, we have two main categories, which are the soft ferrites, which would be the upper curve, and the hard ferrites on the lower curve. The coercivity is the resistance of a magnetic material to changes in magnetization, equivalent to the field intensity necessary to demagnetize the fully magnetized material. Soft magnetic materials are mainly used in inductive components, whereas hard magnetic materials are mainly used as permanent magnets and with electromagnets. As shown in the hysteresis curve, even if the field strength H has returned to zero, magnetic flux B is still present. B sub R is what we call it. However, if we want to reset the flux density to zero, a certain negative field strength has to be applied, which is called the coercive field strength, H sub C. With this in mind, let's analyze soft ferrites, which have low coercivity, meaning that they are easy to demagnetize. An example of this soft ferrite would be manganese zinc and nickel zinc. You can see the behavior on this type of cores on the following animation. It visually shows how easy it is to demagnetize this material. On the other hand, hard ferrites have high coercivity, which means that they are difficult to demagnetize. This is a characteristic of iron powder cores. And here also the animation shows the difference between these two, and you can see the comparison between both of the hysteresis curves. You would need a stronger magnetic field in order to magnetize or demagnetize this type of cores. So how does this translate to the saturation curve? As previously mentioned, the core material is directly related to the saturation current on an inductor. This is the current at which the initial inductance value has dropped by a percentage specified in that sheet. This percentage can range from 10% to 40% and must be carefully checked as the value varies among different components and manufacturers. The following graph shows both materials with their inductance percentage drop and how this is affected by the current flowing through them. Once the saturation current is surpassed, you can see the main differences between them. The red line shows the subferrites. We call this the saturation knee, or hard saturation. Since this material is easy to demagnetize, as previously shown, the inductance value drops almost immediately after the saturation current is surpassed. And the black line shows the hard ferrites. As you can see, the behavior is quite the opposite. We call this subsaturation, due to the fact that the inductance does drop once the saturation current is surpassed. However, due to the high coercivity, this inductance drop is very slow or gentle. Now, let's talk about permeability versus frequency. Permeability can be described as a magnetic conducting or penetrating property, analogous to electric resistance. The relative permeability of the material is not constant, but nonlinear. This behavior is essentially dependent on a couple of factors, such as the magnetic field strength, which is dependent on operating conditions, the frequency, the temperature, and the material. Core materials can only be used effectively in the construction of inductors within a limited frequency range, as a result of the frequency-dependent loss components. Core losses rise sharply above a typical frequency limit. The following graph demonstrates the relationship and the limits of these core materials. It plots the inductive parts of impedance, X of L, and their frequency dependence for 3 different core materials. You can see the comparison between iron powder in the black line, manganese zinc in red, and nickel zinc in green. This test was made at room temperature levels, in this case 25 degrees Celsius. It is worth noting that iron powder materials may be used as pure inductance up approximately 400 kilohertz. The loss component dominates subsequently up to approximately 10 megahertz. This type of core would be ineffective in the frequency range above roughly 20 megahertz. Now, manganese zinc cores are inductive up to frequencies around 20 and 30 megahertz. Losses are usually rising above 10 megahertz, and the core material is no longer effective in the frequency range above 80 megahertz. And finally, nickel zinc cores are inductive up to frequencies around 60 megahertz. If we keep increasing this value, the core material is no longer effective above approximately 1 gigahertz and beyond. So this graph basically demonstrates why nickel zinc ferrites are predominant in the EMC field. The core material can perform an effective filter function in the frequency range of the greatest interest. We can also point out the typical initial permeability values of these cores at this specific test condition. Iron powder cores have a permeability between 50 and 150. Manganese zinc cores are between 300 and around 20,000. And nickel zinc cores would be between 40 and 1500. With that said, let's analyze how the permeability behaves when the core experiences a temperature change. The following graph shows the initial permeability as a function of temperature. This test was made at a frequency of 10 kilohertz. The initial permeability values of each core remain as previously stated. Now, coils having ferrite core materials show a variable inductive behavior with change in the ambient temperature. There are two important concepts to take into consideration. On one hand, the maximum operating temperature range, and on the other hand, the current temperature. It is highly recommended that the temperature of the component does not exceed this maximum operating temperature under worst-case conditions. This range is dependent on core material chemical formula. And, well, the current temperature is the point where the ferrite material loses all its permeability. This is why the inductance drops to zero, as pointed out by the arrow on the graph. However, this condition is not permanent. Once the ferrite cools down, the previous permeability is restored. Generally, the higher the initial permeability, the lower the current temperature. And typically, permeability presents a peak right before the ferrite reaches its current temperature, as you can see on the graph. Great, so now that we have covered the basics of the core materials and what to consider when deciding for a specific application, let's go ahead and talk about the wire and its characteristics. One of the main concepts when we discuss the wire of an inductor is the direct current resistance, commonly found as DCR on the datasheets. We can define this concept as the resistance of an inductor as a result of the resistance of the wire used in the winding. On the following slides, we're going to review how to calculate this resistance value given the two main types of wires, round and flat. You might wonder, which one's better? Well, this entirely depends on the application. There are also a couple of wire characteristics that are going to define the inductor's behavior. This would be the physical size related to the resistance, which affects the current and temperature. The frequency, which is going to produce a skin and proximity effect. And the insulation class, which relates to the voltage. First, let's tackle how to calculate the DCR value on a round wire, which might be the most commonly found. For these examples, we're going to be using a copper wire with a resistivity of 1.68 to the power of -8. This value is assigned to the Greek letter rho, and it is measured in ohms per meter. We would also need the length of the wire, which is the letter L on the formula, and the cross-sectional area, which is A. In order to calculate the direct current resistance, we must use the shown formula and always remember to convert all parameters to meters. First of all, let's propose a diameter of 1 millimeter, as shown on the little yellow circle on the bottom left corner. We can easily calculate the cross-sectional area with this information. We take the 1 millimeter diameter squared, multiplied by pi, and divided by 4. That's how we get the 0.78 square millimeters as the cross-sectional area. After this, we can substitute the values on our formula, as shown on the right side of the slide. We must multiply the resistivity of copper times the length of the wire, which for this example is 1 meter, and finally dividing this result by the cross-sectional area that we have previously calculated. The final result would be 21.5 milliohms for the direct current resistance when there is a 1 millimeter diameter. As you can see, the bigger yellow circle on the bottom left corner shows a diameter for 2 millimeters. And we've applied the same calculations and we got the following results. the cross-sectional area is 3.14 square millimeters, and the direct current resistance would be 5.35 milliohms, which is around 4 times smaller than the previous calculation. And this is considering the same wire length and material. With this example, is shown that the bigger the diameter, the bigger the cross-sectional area. Therefore, the direct current resistance would be smaller. Of course, you could adjust any of these variables in order to get different DCR values. This formula is quite helpful for this. Okay, so now that we have shown how to calculate the DCR value on round wires, let's dive into flat wires. For this example, we're once again using copper as our wire material. This means that the resistivity rho stays the same, 1.68 to the power of -8. Also, we have a 1 meter long rectangular shaped wire with a cross-sectional area of 4 square millimeters. The width of this rectangle measures 4 millimeters and it is 1 millimeter in height. As you can see, the same principle applies, and formula, of course, in this type of wires. On the right side, you can see the procedure to calculate the direct current resistance. We must multiply the resistivity of copper times the length of the wire, which for this example is also 1 meter, and finally dividing this result by the cross-sectional area that we have previously calculated. The final result would be 4.2 milliohms, which is a bit lower than the 2 diameter round wire on the previous example with 5.35 milliohms. So now that we have calculated the direct current resistance for both types of wires, round and flat, you might be wondering why we got these results. And the answer is, this is entirely related to the cross-sectional area that both geometric shapes possess. The following example shows the comparison between both shapes with similar dimensions. We have the yellow circle with a 1 millimeter diameter and a blue square with each side measuring 1 millimeter. Due to these geometrical properties, the circle has approximately 78% area compared to a similar width square, meaning that the circle loses about 22% surface area. This is shown on the right figure when we overlap both shapes. Each square corner has around 5.5% more area. So this is the reason why the yellow circle has a cross-sectional area of 0.78 square millimeters, and the blue square has a slightly bigger value, 1 square millimeter. Since this value is higher, the direct current resistance value would be lower, as shown below, with 21.5 milliohms on the yellow circle and 18.3 milliohms on the blue square. Great, so let's go back to the basics and quickly recap this information. As the cross-sectional area increases, the direct current resistance is reduced, as shown on the graph. In other words, the direct current resistance is inversely proportional to the cross-sectional area of the conductor. The larger the cross-sectional area of the conductor, the more electrons are available to carry the electric charge, hence the low resistance. You can see below the 3 examples that we have previously analyzed. There is another important concept to talk about when we refer to frequency and alternating current losses. This is called the skin effect. For single isolated conductors through which high frequency current flows, current only flows on the outer skin of the conductor. In other words, as we increase the frequency, the current starts to get pushed on the outer wire layer, which means that it has less space or area to flow through. The yellow figure on the right shows the cross-sectional area of a round wire with diameter d, radius r, and penetration depth delta. Most current flows on this outer ring delimited by the delta value, or as we call penetration depth. In order to calculate this penetration depth, we would need to have the permeability and resistivity of the wire material. Also, the angular frequency, which can be calculated by multiplying 2 times pi times the frequency of operation. For this example, we're going to be using copper as our wire material with the shown properties. We would only need to follow the shown formula in order to obtain the penetration depth, which for this example is measured in meters. Great, so let's evaluate the skin effect in an application. If we have a buck converter with a 250 kilohertz frequency and we're using a round copper wire, this would be the way to calculate the penetration depth. First of all, we take the resistivity of copper, rho, and multiply it by 2. After this, we would need to divide it by the result of 2 times pi times the 250 kilohertz frequency times the permeability of copper. The result would be 17 to the minus 9th power, which we would need the square root. After substituting the values in the formula, we have that the penetration depth for this buck converter would be 0.13 millimeters. So what does this mean? The following diagram shows the current distribution in a conductor at various frequencies. As this frequency increases, the skin depth decreases, and the cross-sectional area decreases as well, therefore increasing in resistance. You can calculate this cross-sectional area by multiplying 2 times pi times the radius times the skin depth. The diagram shows 3 examples of this skin effect. As you can see, at 50 Hz, we have a 9.38 millimeters skin depth. If we increase the frequency to 10 kilohertz, the skin depth would be less, 0.66 millimeters. And finally, if we increase it to 400 kilohertz, the skin depth would be even smaller, 0.1 millimeters. The area at which the current flows is going to be limited by this value. This is something very important to take into consideration when handling high frequency values. With that said, let's talk a little bit more about the rated current. Würth Electronic defines rated current as the current that causes the inductor to heat up above ambient temperature due to self-heating. This is different from saturation current and may be a larger value. For example, if an inductor is operated at its rated current, it means that it heats up above the ambient temperature by the temperature stated in the datasheets. In our components, this stated temperature is typically 40 degrees Celsius. However, magnetics industry is not standardized, and not all manufacturers use the same testing parameters on their datasheets. This is always something you must take into consideration when comparing inductors between different competitors. The diagram on the right shows our measurement setup to determine the rated current. We place the inductor with a sensor on a testing bench and power it with, of course, a power supply. We use a temperature sensor device to detect the ambient temperature and the inductor's temperature. All this information is analyzed and saved in a computer. And finally, let's discuss the self-resonant frequency. Every inductor has a capacitive coupling arising from its winding turns and multiple layers. These parasitic capacitances are symbolized by a capacitor C in the equivalent circuit shown on the top right diagram. This capacitance in the coil forms a parallel resonant circuit with the inductance. The self-resonant frequency, or SRF, is the frequency at which the parasitic capacitances of the inductor resonate with the ideal inductance of the inductor. The input energy oscillates back and forth between the elements of inductance and capacitance. The inductor only functions of the self-resonant frequency. If the inductor is operated above its resonance, the capacitance dominates, and in fact, the inductor acts as a capacitor. This is why they should always be operated below their resonant frequency. Also, at the self-resonant frequency, the impedance becomes very high, and the inductor can be used as a EMC filter choke. Take in mind that the higher the number of turns around a core will result in a higher inner winding capacitance. Therefore, this shifts the self-resonant frequency into the lower frequency spectrum. Okay, so thank you very much for your kind attention during this webinar. Now let's go ahead and answer some of your questions. Seems like we have a question here. Okay, so we have one question that says, what's the main characteristic of power inductors? Larger saturation current? Well, we could answer that also referring to the Q factor. As we said during the presentation, you would want a high Q factor so the inductor acts as an ideal inductor if you want it as a storage inductor. You would need a low Q factor when you need filtering applications. So that's how I would answer that. And also not necessarily related to the saturation current. Okay, let's check another question. Okay, so we have a question that says toroids versus others. Which one reduces the capacitance better? So this is related to this last slide that we see. It would depend also on the number of turns that you have around the core. So of course, if you have a big amount of turns on the core, this is going to result in a bigger inner winding capacitance. Okay, it seems like we have a question about the high frequency applications. We would recommend to use flat wire instead of round wire due to the skin effect application. Okay, this one is interesting. Can we touch on permeability and iron powder composite cores again? What are the critical factors we need to look for to avoid wear permeability? So, as we mentioned, permeability is affected mainly by frequency and temperature. So those would be the two main factors. Also, when you have the iron powder cores, let me see if I can go back here into the presentation. Okay, so yeah, iron powders are hard ferrites, so they have high corrosivity and they are difficult to demagnetize. So that's why if you overpass the saturation current, you're not gonna see a significant drop right away if you overpass that saturation. So that's, you shouldn't have much problem if you go over that saturation if you use iron powder cores. Because if you use the other ones, the subferrites such as the manganese zinc or the nickel zinc, you would have that saturation need that we explained. So hopefully that solved the question. Okay, let's go ahead and check another one. And of course, just a little note on the iron powder. Iron powder is better at operation at low frequency. Okay, there's one question. Does Word offer a calculator for creating filters? We have a program that we call Red Expert. I'm not sure if you've heard about it, but you could go online on the catalog and you could see it right there. It's Red Expert. You click on it, you can select power inductors, and that's gonna get you basically every inductor that we have at Word. With that, you can see how it works with current, what would be the saturation, how does it respond to frequency, etc. So that would be the best way for you to know how to operate the inductor without necessarily physically doing a circuit. You could basically simulate that kind of stuff on Red Expert. Great question. Okay, there's one last question, I believe. Someone asks, am I correct that power inductors that are intended for higher frequencies can use wire with a smaller cross-sectional area because of the skin effect? Is this why some power inductors I've seen in things like blade server power supplies have flat wires? And yeah, I mean the answer would be yes. As we show on the presentation, round wires have the skin effect at higher frequencies. If you had flat wires, you wouldn't necessarily be worrying about the skin effect. So yeah, I mean that might be the reason. Okay, it seems we have one more question. Do inductors have polarity? And the answer is yes. Inductors do have polarity. There is a start and finish to every winding, and winding clockwise or counterwise will change the polarity. So that would be the reason why. Thanks a lot for coming to this webinar. Have an excellent day and thank you for coming.